Okay, so let's take another look at the same two directed line segment vectors that we looked at in part 1. And we'll remind ourselves that they have a horizontal component, or a delta x of 3, a vertical component, or a delta y of 2. They both have that. So they had the same length as we calculated in part 1. But they are in different locations. Obviously, P is in a different place than R. The initial points are the same, the initial points are in different locations. But again, they have that same delta x and delta y, the horizontal and vertical components. So it's convenient to write all vectors in what's known as component form, where we're mostly just concerned about this delta x and delta y value, the horizontal and the vertical component. So component form is basically putting every vector that we encounter into what's known as standard position. Now, standard position is where the initial point is on the origin. So this vector u, as we said, is in standard position. The initial point is on the origin, so vector u is in standard position already. And what that enables you to do is the terminal point itself here gives you that horizontal and vertical component, whereas this one, vector v, you didn't have that. You had to calculate it each time, or count boxes, or however you got there. So one thing we're going to do is put pretty much every vector we encounter into component form, which it's a moderately easy calculation to make. The component form of a vector with initial point P and terminal point Q, basically what you're going to do is point P, it has the ordered pair P1, P2. Point Q has the ordered pair Q1, Q2. And what you do is you do the terminal point minus the initial point to get the x and y components of that vector. The big key, the big takeaway is terminal minus initial is the way we're always going to calculate that component form. And now that we have this vector listed in component form, now if you look in your textbook, you'll see that vector v here has components v1, v2. I like to ease it up and say, we're just going to call it the x and y components, x being the horizontal component, y being the vertical component, of course. So now that you have it in that context in xy, calculating the magnitude or length, if you recall, we did the Pythagorean theorem when it was just a line segment. But now that we have it, we can calculate the magnitude using a quick formula. What you'll notice is the horizontal component, whether it's Q1 minus P1, whether it's V1 or whether it's X, it's delta X squared, delta Y squared. So essentially what this is the Pythagorean theorem adapted for vectors, adapted for magnitude. So it all comes back to Pythagorean theorem. And by the way, this little notation here means the magnitude of vector v. And you'll see that come up all over the place in this unit. So get used to that little two pairs of vertical lines meaning magnitude. All right, so there's your how to find your component form and your magnitude. So what we're going to do, let's go ahead and look at an example of computing the component form and the magnitude of a vector. So we've got a vector. It starts at point 4, -7. It ends at point -1, 5. So let's get a quick sketch of that. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. There's point 4, -7. And now, again, this is just a quick sketch. And so the vector itself is the directed line segment that connects the initial point to the terminal point. So let's grab a little straight edge here to make it look pretty. So that's our vector. And we want to write it in component form. And now component form is going to describe the delta x. There's your delta x. And the delta y. Here's your delta y. and list it independently like that. So again, the operative word here, the operative phrase, however you want to put it, you're always going to do terminal minus initial when you're finding the component form. And so let's do it. We're going to call this one vector v, because the first letter in the word vector is v. And it's always the terminal minus the initial. So we're going to do -1 minus 4. We're going to do 5 minus -7. We're going to simplify as much as we can, which is not really terribly complicated in this instance. So we get vector v in component form to be -5, 12. And that is vector v in component form, and that describes the delta x of -5 units and the delta y of positive 12 units. So that actually gives it that direction. -5 means move to the left, positive 12 means move up. All right, so there is the component form. Now we need to do the magnitude. So let's go ahead and do that, the magnitude, using our new little notation. And now that we have it in component form, let's just go right to that easy version of the formula, rather than, you know, messing around with Q1, P1, P1, all that kind of stuff. Keep it easy. And so the magnitude of vector v is 13 units, because the square root of 169 is exactly 13 units. So what that means is that this is 13 units long, so the magnitude of that vector. And what you can hopefully recognize is that Pythagorean triple, because horizontal and vertical are always right angles. So vectors do relate back to all of the right triangle trigonometry that we've done so far this